Hello friends, today's question. A load of mass m kg is suspended from a steel wire of length 2 meter and radius 1 mm in Searle's apparatus experiment. The increase in length produced in the wire is 4 mm. Now the load is fully immersed in liquid of relative density 2. The relative density of the material of the load is 8. The new value of increased in length of the steel wire is. So in this case, it is basically a combination of using the Young's modulus of elasticity formula along with the buoyant force. And in this case, for the density of liquid, it is given the relative density, so that the relative density is with respect to water, and also the material density is given as a relative, that is 8, and that is also with respect to the relative density of the water. So that is a common factor between the two. So in this case, first of all, we are going to find out the, you can say, extension when it is outside the liquid. Then we are going to find out extension when it is inside the liquid, and we are going to make a comparison between the two, and it is going to help get the answer, that is increase in length, new value when it is submerged in the liquid. So let us start when it is suspended in the air outside the liquid basically. So we can say that effective force acting on the load and in the first case we are going to find whenever it is outside the liquid. Okay, then we are going to find out when it is inside the liquid. So in the first part we are going to say the initial force acting on the load. Initial force acting on the load. Here initial means outside the liquid. Outside the liquid, and which will be nothing but weight of the liquid. So we can write this as m is the mass and g is the acceleration due to gravity. And when this load is immersed in the water, a liquid rather, then the effective force that will be acting on the load will be reduced because of the buoyant force which will be acting in the upward direction. So you can say when the load is immersed in the liquid, the effective force is reduced by the buoyant force. So therefore, we can write that our F effective will be equal to mg minus the buoyant force, which is represented as Fp, buoyant force. Therefore, we can write that we will sort out this equation later on. Okay, so first of all, let's find out what will be the you can say the volume of the load. Then we are going to find out the buoyant force and use this particular equation to solve it. So let us call this equation number 1. Next, we find out, let us calculate the volume of the load. Calculate volume of the load. And in the question itself, we are given that the relative density of the load is the ratio of the load's density to the density of the water. So in the question we are given that the relative density of the load, relative density of the load, and that will be equal to ratio of load's density to the density of the water. Density of water. So it means the density of the load is, suppose, rho load, then it will be equal to 8 multiplied by density of the water, because the ratio relative density is given as 8. Okay. And from here we can find out that the volume of the load, will be equal to, let us suppose that is given as V, and that will be equal to mass of the load divided by its density. And we are going to get this as mass divided by 8 multiplied by density of the water. And density of water is 1000 kg per meter cube. So we can write that volume is equal to M 8 into 1000. So this is the volume of the load. Now let us find out what will be the buoyant force which will be acting on the body. So next is calculate the buoyant force. Buoyant force. So when the load is immersed in the liquid, it experiences a buoyant force, and the value of the buoyant force will be equal to the weight of the liquid displaced by the load. So we can write that when the liquid is when the load is immersed in the liquid, it experiences a buoyant force. And the buoyant force is equal to the weight of the liquid displaced by the load, is equal to the weight of the liquid displaced by the load. So buoyant force we know is represented as FB, so we can write our FB will be equal to density of the liquid multiply volume of the load and multiply by G. And the relative density, the density of the liquid is also given in the relative term. So we can write that the density of the liquid is equal to twice multiplied by density of the water. And density of water is, we know, is 1000, so this will be 2 multiplied by 1000. Therefore, we can write that our buoyant force Fp will be equal to 2 into 1000, and volume we just calculated is m upon 8 into 1000 and multiply by g. 1000 and 1000 goes away, and this comes as 4. So we get this will be equal to 1 by 4 mg. So we are going to use this value of buoyant force. Let me write it here. Fp is equal to 1.4 mg. Let us call this as equation number 2. So therefore, now we are going to use equation number 2 in equation number 1. And equation number 1 was our that the effective force will be equal to mg minus the buoyant force. You can write from equation 1 and 2. From equation 1 and 2, we get F effective will be equal to mg minus 1 by 4 mg, and this becomes 3 by 4 mass of the load multiplied by g. So this is the effective value of the force that will be acting on the load when the load is immersed in the liquid. Now let us find out what is the relationship between the force and the elongation. Okay. The relationship between force and elongation. And we also know that from the Young's modulus that the elongation of the wire is proportional to the force applied. So we can say that the elongation of the wire is proportional to the applied force applied. So we know that F upon A is equal to Y delta L upon L. And in the question itself, it is given that the initial elongation is 4 mm. And the elongation is represented as delta L. So we can say that initial elongation when force is our mg, and this is equal to 4.0 mm, and let us call that delta L initial. And new elongation when the force is the F effective, you can say new elongation when force is F effective, that is 3 by 4 m into g, and that is, let us suppose, is given as delta L nu, which we are supposed to find out. Okay, and according to just I said that the elongation of wire is directly proportional to force applied, so we can say from here that the ratio of delta L nu divided by delta L initial will be equal to delta L nu. The force is our 3 by 4 mg, and for delta L initial the force is given as mg. So mg and mg cancels out, and this comes as 3/4, and L initial is given as 4 millimeter. So we can write that delta L nu is equal to 3 into 4, and this is in millimeter. So 4 and 4 cancels out, so therefore we get the delta L nu is 3 millimeter, and this is our new value of increased length in the steel wire. So you can say delta L nu is equal to 3 millimeter, and this is the new value of increase in length. Increase in length of the steel wire. Steel wire. So if the options are available to us, the option number D is the correct option. So you can say option D is correct. Okay. So this completes the question. Thank you.